Welcome to these gentle, soothing stories for sleep. Tonight, we will begin a journey together, a slow drift into the quietest and most profound depths of the cosmos. We will not be exploring the loud, bright, and chaotic parts of our universe, but instead, we will seek the comfort of its deepest silence, finding a strange and beautiful peace in the silent mysteries of black holes. Our story is not one of fear, but of wonder, a tale of how the greatest emptiness can hold the greatest meaning, and how by contemplating these distant, silent giants, we might calm the quiet corners of our own minds. Before we begin our journey into the stellar dark, I would love to know where you are listening from tonight, or perhaps how your day has been. Please feel free to leave a gentle thought in the comments below. And if these stories bring you comfort, please support this channel with a like and a subscription. Thank you so much. Now, find a comfortable position, close your eyes, and allow your breath to slow. As we drift into the darkness, a darkness not empty, but full of stars waiting to be born. Our journey begins in a place of immense and gentle beauty, a vast cosmic cloud stretching for light years across the silent tapestry of space. It is a stellar nursery, a place like the Great Orion Nebula, a luminous stain of pastel pinks and deep violets against the velvet black. Imagine yourself floating here, weightless and calm, surrounded by wisps of ancient hydrogen gas, the oldest element in the universe, mingled with the delicate dust of carbon and silicon, the very same elements that form our world and our bodies. This is not an empty place, but a place of infinite potential, a celestial womb, where gravity, the gentlest and most patient of cosmic forces, is beginning its slow and tireless work. Over millions of years, it gathers these ethereal threads together, pulling them into ever so slightly denser pockets, whispering them toward a common center. There is no rush here, only the unhurried, graceful dance of attraction, a quiet coming together that will eventually form a new star. This process is like the slow gathering of morning mist over a still lake, a gradual coalescing that seems almost magical, yet it is guided by the most fundamental and dependable law of the universe. It is a reminder that the grandest creations often have the quietest and most humble beginnings, starting from almost nothing, just a slight disturbance in the cosmic dust, a gentle pull in the endless dark. As you drift through this soft, glowing cloud, you can almost feel the process unfolding. A region within the nebula begins to grow heavier, denser, its gravitational influence expanding like a silent ripple. It draws more gas and dust into its embrace, not with violence, but with a persistent and irresistible invitation. This growing core is a protostar, a star in its infancy, not yet luminous with the fire of fusion, but glowing with a soft, deep red warmth from the friction of its own gathering. It is the embryonic heart of a new sun, slowly contracting under its own immense weight, its temperature steadily rising over thousands and thousands of years. We can think of this phase as a long, slow inhalation, a gathering of strength and substance before the star truly awakens. It is a period of quiet formation, a testament to the power of patience, showing us that even in the vastness of space, things take time to grow into their true form. This gentle glow in the heart of the nebula is a promise, a beacon of the brilliant life that is to come. A life that will one day pour light and warmth into the surrounding darkness, creating a small island of order and energy in the vast ocean of the cosmos. And then, after a long and patient childhood, the moment of awakening arrives. In the very center of the protostar, the pressure and temperature reach a critical point, a threshold of millions of degrees, and something extraordinary happens. The hydrogen atoms, once drifting freely, are now crushed together with such incredible force that they fuse, merging to become helium. This is nuclear fusion, the engine of the stars, and in this instant, a colossal amount of energy is released. The star is born. It ignites, pushing back against the relentless crush of gravity with an outward torrent of light and heat, establishing a perfect and delicate equilibrium that it will maintain for most of its life. This is the star's first breath, a silent, luminous exhalation that will continue for millions, or even billions, of years. It settles into a long and stable maturity, a shining example of balance, the inward pull of gravity perfectly matched by the outward push of its own radiant heart. For a time, it is a constant, a reliable source of light, a celestial anchor in the ever-changing cosmos, and it is in the fiery hearts of stars, much larger than our own sun, that the true alchemy of the universe takes place. Within the core of this massive, brilliant star, the process of creation continues. As it burns through its hydrogen, it begins to fuse helium into heavier elements like carbon and oxygen. And as the star ages, its core becomes a layered, cosmic forge, creating progressively heavier elements: neon, magnesium, silicon, and finally, iron. Think of this for a moment: the calcium that gives strength to your bones, the oxygen you are breathing in right now, the iron that courses through your veins, giving your blood its rich, red color. Every single one of these vital atoms was forged in the heart of a star that lived and died long before our Earth was ever formed. We are, in the most literal sense, made of stardust. We are the living, breathing legacy of these ancient stellar furnaces. This deep and profound connection ties us to the most distant objects in the night sky, reminding us that we are not separate from the universe, but an intimate and inseparable part of its grand, unfolding story. Our existence is a testament to the lives of these stars, their light, and their eventual, transformative darkness. And it is the fate of the most massive of these stars that sets the stage for our journey. For their brilliant lives must end, and in their magnificent farewell, they leave behind the seeds of the greatest mystery of all. And so, this luminous life, so brilliant and vast, carries within its core the seed of its own magnificent conclusion, a destiny woven from its own immense mass. While smaller stars like our Sun will fade gently over billions of years, the most massive stars, the brilliant blue giants that burn 100 times brighter, live a much shorter and more dramatic existence. Their incredible luminosity is fueled by a ferocious rate of nuclear fusion, causing them to consume their vast stores of hydrogen in a mere few million years, a fleeting moment in cosmic time. Imagine their lives not as a long, steady candle flame, but as a brilliant and breathtaking firework, a short-lived but utterly spectacular display of celestial power. Their very brilliance is a sign of their impending demise, a glorious sprint rather than a slow marathon. These stars are the great alchemists of the galaxy, and their frantic pace of creation, forging element after element in their layered cores, is a race against the unyielding force of their own gravity, a force that will ultimately, and inevitably, claim victory in the end. This dance between the outward fire of fusion and the inward crush of gravity is the central drama of a star's life, a perfect tension that cannot last forever. The journey towards darkness begins deep within the star's core, where the stellar forge has completed its greatest work. After creating a sequence of ever heavier elements, the fusion process finally arrives at iron. Here, the alchemy stops. Unlike the lighter elements, the fusion of iron atoms does not release energy. It consumes it. This means the furnace at the heart of the star, the very engine that has held it up against its own weight for millions of years, suddenly and catastrophically switches off. The outward pressure of radiation ceases, and the delicate balance is shattered in an instant. For a moment, the star hangs in suspense, its heart no longer beating, its source of support gone. Gravity, the patient, relentless force that has been waiting all this time, now becomes utterly dominant. The iron core, now inert and unimaginably dense, has nothing left to hold it up, and in less than a second, it collapses in upon itself with tremendous force. The star that was once a symbol of expansive, radiant energy now begins a final, swift journey inward. A journey into silence and density, a profound and irreversible surrender to the fundamental curvature of spacetime that it has created. This catastrophic core collapse triggers the most spectacular event in the known universe, a core collapse supernova. As the star's outer layers, containing trillions of tons of gas, come crashing down toward the center at a fraction of the speed of light, they slam into the newly formed, incredibly dense core. This core, which has been squeezed into an object only a few kilometers across, but containing more mass than our Sun, is so rigid that it acts like a cosmic anvil. The infalling material rebounds, creating a colossal shockwave of energy that begins to tear through the star from the inside out. This shockwave, energized by a flood of ghostly particles called neutrinos, blasts the star's outer layers into space in a silent, luminous explosion of unimaginable scale. For a few weeks, the dying star can outshine its entire host galaxy, a final, magnificent flare of glory. This is not an act of pure destruction. It is a profound act of creation and dispersal. The supernova seeds the surrounding cosmos with all the heavy elements that were forged within the star's core, enriching the interstellar clouds with the raw materials needed for new stars, new planets, and perhaps new life. It is the star's magnificent farewell, its ultimate gift back to the universe. And what is left behind, in the quiet aftermath of this luminous spectacle? The fate of the collapsed core depends entirely on its mass. If the remnant is below a certain critical threshold, known as the Tolman-Oppenheimer-Volkoff limit, roughly 2 to 3 times the mass of our Sun, the collapse is halted by a quantum mechanical principle. The particles of the core are squeezed so tightly together that they can be squeezed no further, forming an incredibly dense object called a neutron star. But if the core's mass is greater than this limit, no known force in the universe can stop the collapse. Gravity wins. Absolutely. The core continues to crush inward, past the density of a neutron star, past any state of matter we can describe or comprehend, collapsing seemingly forever toward an infinitely dense point. In this moment of ultimate defeat for matter and ultimate victory for gravity, a black hole is born. The supernova shines brightly for a time, but its light eventually fades, leaving behind this new and permanent feature in the cosmos. An object whose gravitational pull is so immense that nothing, not even light itself, can escape its grasp. It is the serene, silent heir to a brilliant life, a place where the familiar laws of physics come to an end, and our journey into mystery truly begins. This quiet victor, this force of gravity that has sculpted the fate of the most massive stars, is a presence so familiar to us in our daily lives that we often forget its profound and cosmic nature. We feel it as the gentle weight of a blanket, the reassuring contact of our feet upon the floor, the predictable arc of a thrown ball returning to the earth. For centuries, our understanding of this force was shaped by the genius of Isaac Newton, who envisioned it as a universal, invisible pull, a mysterious set of ropes connecting every object in the cosmos to every other object. He imagined the sun holding the earth in its orbit, with an unseen tether stretching across 93 million miles of empty space, a constant and unwavering attraction that dictated the elegant clockwork of the solar system. This was a revolutionary and beautiful idea, one that brought order to the heavens and the earth under a single, elegant law. And yet, a deep question remained at its heart. How did this force act across the void? How did the sun communicate its presence to the earth with no medium to carry the message? It was a mystery of action at a distance, a ghostly influence that worked perfectly in the mathematics, but defied easy intuition. It would take another 2.5 centuries for a new vision to emerge, a vision that would completely reshape our understanding of the universe and the nature of gravity itself. Through the mind of Albert Einstein, gravity was transformed. It was no longer a force, not a pull or a tether, but something far more intimate and fundamental. It was, he proposed, a consequence of the very shape of the universe. Einstein asked us to imagine that the 3 dimensions of space and the single dimension of time are not separate entities, but are woven together into a single, dynamic, 4-dimensional continuum called spacetime. This is not a passive backdrop, not a static stage upon which the cosmic drama unfolds, but an active participant in the story of the universe. He revealed that this fabric of spacetime is not rigid and flat, but soft and flexible, capable of being bent, curved, and warped by the presence of mass and energy. It is this curvature, this geometry of the cosmos, that we perceive as gravity. The universe is not empty, it is a landscape, and it is the contours of this landscape that guide the motion of everything within it. To help our minds grasp this beautiful and abstract idea, we can use a simple, calming analogy. Picture a vast, soft sheet of fabric stretched perfectly taut and flat, representing the unperturbed fabric of spacetime. Now, imagine placing a heavy ball, like a bowling ball, in the center of this sheet. The weight of the ball creates a gentle, smooth depression in the fabric, a curve, a dip, centered on the ball. This is what a star or a planet does to the space-time around it. It creates a gravitational well, a gentle valley in the cosmic landscape. If you then take a much smaller marble and gently roll it across the sheet near the heavy ball, the marble will not travel in a straight line. Instead, it will follow the curvature of the fabric, spiraling inward, circling the central depression. To an outside observer, it would look as though the large ball is pulling the marble towards it, but in reality, the marble is simply following the straightest possible path available to it through a curved surface. There is no mysterious force at play, only the elegant and inevitable consequence of geometry. This is the dance of the planets around the sun, a silent, graceful waltz dictated by the gentle curves in space-time. This natural path, this line of least resistance that all objects follow through the curved landscape of the universe, is known as a geodesic. A planet in orbit is not being constantly pulled off course by the sun. It is simply drifting along its natural geodesic through the space-time that has been shaped by the sun's immense mass. Light from a distant star, as it travels across the cosmos, also follows these geodesics, its path bending as it passes through the gravitational wells of galaxies and other massive objects. This transforms our perception of motion in the universe from a constant struggle against an invisible force to a state of effortless, natural flow. It is a cosmic principle of surrender, of following the path that has been laid out by the very structure of reality. And this brings us back to the silent remnant of our collapsed star. A star or a planet creates a gentle dip in the fabric of space-time. But a black hole is something else entirely. It is what happens when a colossal amount of mass is concentrated into an impossibly small space, creating a curvature so extreme, a gravitational well so deep and steep, that it is less like a valley and more like a puncture, a bottomless abyss from which there is no upward path, no geodesic that leads back out into the universe. And in this cosmic landscape of gentle hills and valleys, the black hole represents something else entirely. A well so deep, a curvature so profound, that the fabric of space-time itself seems to cascade infinitely downward. At the very heart of this abyss lies a concept that challenges the limits of our imagination and our physics: the singularity. According to our current theories, the singularity is the final destination of all the matter that made up the star's core, crushed into a region of zero volume and infinite density. Here, at this theoretical point, the curvature of space-time becomes infinite, and all the known laws of nature, the elegant equations of general relativity that describe the universe so well, simply break down. They cease to provide answers, dissolving into mathematical infinities. We should therefore think of the singularity not as a literal, physical object that we can picture, but as a boundary to our own understanding. It is a point of ultimate mystery, a silent, final confession from the universe that there are some places where our current stories and maps are no longer valid. It is a place of profound quiet, where the language of physics falls silent, inviting not fear of the unknown, but a deep and humbling awe for the vastness of what we have yet to comprehend. While the singularity itself remains a theoretical enigma, shrouded from our view, the black hole does have a tangible and well-defined boundary, a threshold that marks its presence in the universe. This boundary is known as the event horizon. It is not a solid surface, not a physical membrane that one could touch, but rather a one-way door in the very fabric of space-time. The event horizon is the precise location surrounding the singularity, where the gravitational pull becomes so overwhelmingly strong that the escape velocity, the speed required to pull away from it, exceeds the speed of light. Since nothing in the universe can travel faster than light, anything that crosses this boundary, be it a particle of dust, a wandering star, or a beam of light itself, can never escape. It is irrevocably captured. We can visualize this by imagining a wide, calm, and powerful river. Far upstream, the current is gentle, and a strong boat can easily navigate or turn back. But as the river flows, it narrows and quickens, and there comes a point, a line across the water, where the current flows faster than any boat could possibly travel. This is the event horizon. A boat can drift across this line smoothly, its passengers feeling no jolt or impact. But once they have crossed, there is no turning back. They are destined to follow the current to its inevitable conclusion. This is the nature of the event horizon. A quiet, calm, and absolute point of no return. The size of this silent shore is determined by a simple and elegant rule known as the Schwarzschild radius, named after the physicist who first solved Einstein's equations to describe it. This radius, which defines the location of the event horizon, is directly proportional to the mass of the black hole. A small, stellar mass black hole, just a few times the mass of our Sun, might have an event horizon only a few miles across. A supermassive black hole at the center of a galaxy, containing the mass of billions of suns, could have an event horizon so vast that it could swallow our entire solar system. This simple relationship brings a sense of order to these otherwise chaotic-seeming objects. It tells us that despite their exotic nature, they are governed by predictable principles, their most fundamental feature, their size, being a direct reflection of the amount of matter they contain. This predictability is a comforting thought, a sign that even in the most extreme corners of the cosmos, a deep and underlying order prevails. This idea of cosmic simplicity is taken even further by a profound concept known as the no-hair theorem. This theorem suggests that once a black hole forms and settles down, it becomes an object of almost perfect simplicity. All of the incredible complexity of the star that formed it, its chemical composition, its intricate structure, the shape of the nebulae from which it was born, is completely lost. The final black hole can be described by just three, and only three, external properties: its total mass, its total electric charge, and its angular momentum, or spin. All other details, all the hair, is radiated away or swallowed. This is a cosmic act of profound purification, a return to an elemental state. It is as if the universe takes the most complex and detailed of stories and edits it down to a single, perfect, and simple word. The black hole is a state of deep equilibrium, a silent sphere of pure space-time curvature, unburdened by the clutter of a complicated past. And as we contemplate this sphere of perfect darkness, this object defined only by its silent horizon, a natural question arises. If it reflects no light and emits no signal from within, how can we possibly see it? How does this invisible object make its quiet presence known to the rest of the waiting universe? This sphere of perfect darkness, though it swallows all light that touches it, reveals its presence not by what it emits, but by how it profoundly shapes the universe around it, especially in how it guides the path of light that passes nearby. Light, that ancient cosmic messenger, travels through the universe in the form of tiny, massless particles called photons, and just like a rolling marble or an orbiting planet, these photons must follow the contours of space-time. They travel in what they perceive to be a perfectly straight line, but when that line passes through the deep gravitational well created by a massive object, their path is inevitably bent. A black hole, with its extreme curvature of space-time, acts as the ultimate cosmic lens, a silent and powerful tool of distortion that alters the appearance of the universe behind it. It is a beautiful and subtle effect, a way for the black hole to sign its name upon the cosmos, bending the very light we use to see, and in doing so, betraying its own invisible location. It's as if the darkness itself is reaching out to gently redirect the messengers of light, changing their stories and creating new and beautiful patterns for us to observe from afar. This phenomenon, known as gravitational lensing, is one of the most elegant and powerful predictions of Einstein's theory of general relativity. Imagine looking at a distant candle flame through the curved base of a wine glass. The flame's image becomes warped, stretched, and perhaps even multiplied. In the same way, a black hole, or any massive object like a galaxy, acts as a natural lens in space. When light from a very distant galaxy travels towards Earth, and its path takes it close to an intervening black hole, the gravity of the black hole bends the light rays, redirecting them. From our perspective on Earth, it appears as if the light is coming from a different location, or from multiple locations at once. The image of the distant galaxy is magnified, brightened, and smeared into strange and beautiful new shapes. This cosmic optical illusion is not a trick. It is the true path of light through a warped and dynamic space-time. It is a direct, visual confirmation that mass guides light, and that the deepest gravity can create the grandest images, painting the sky with the light of galaxies that might have otherwise been too faint or too distant for us to ever see. When the alignment of the distant light source, the gravitational lens, and the observer on Earth is almost perfect, the results are particularly breathtaking. In such a case, the light from the background galaxy can be smeared into a near-perfect circle of light, known as an Einstein ring. It is a celestial halo, a golden ring of a distant galaxy wrapped perfectly around the invisible foreground object. It is as if the black hole has become a cosmic artist, using the light of an entire galaxy as its paint to draw a perfect circle on the canvas of the sky. More often, the alignment is not quite so perfect, and the distant galaxy's light is stretched and distorted into luminous arcs and multiple distorted images, like reflections in a cosmic hall of mirrors. Astronomers can study these beautiful arcs to map the distribution of mass in the lensing object, even the parts that are completely dark, like black holes or the mysterious dark matter. These gentle, bending arcs of ancient starlight are therefore the black hole's graceful fingerprints, the silent, elegant evidence of its immense gravitational presence. For decades, this was how we hunted for these invisible giants, by observing their subtle, artistic influence on the light that passed them by. But in the year 2019, humanity achieved something truly remarkable. Using a global network of radio telescopes working in unison, a project known as the Event Horizon Telescope, we managed to capture the first ever direct image of a black hole's immediate surroundings. We looked at the supergiant elliptical galaxy Messier 87 and saw not the black hole itself, but its silhouette, its shadow. What the image revealed was a glowing, blurry ring of superheated gas swirling in a brilliant accretion disk around the event horizon. A final, luminous scream from matter being drawn into the abyss. And in the center of that glowing ring was a perfect circle of pure darkness. That darkness is the shadow of the event horizon, the region where light can no longer escape, the direct visualization of the point of no return. We had finally seen the shape of the abyss. It was a profound and humbling moment, a testament to human ingenuity, allowing us to see an absence, to photograph a silence, and to confirm that these silent shadows, some of them of an unimaginable scale, are truly out there. The silent shadow we finally witnessed in the heart of that distant galaxy, M87, belongs to a class of object far grander and more ancient than the lonely remnants of a single star, revealing that black holes exist on truly astonishingly different scales. The one born from the supernova we imagined earlier, with a mass perhaps 10 or 20 times that of our Sun, is known as a stellar mass black hole. These are the common nomads of the cosmos, scattered throughout galaxies like solitary, dark seeds sown by the deaths of massive stars. But the giant in M87, with a mass of over 6 billion times our Sun, belongs to a much more majestic and mysterious class. The supermassive black holes. These colossal entities are not wanderers. They are anchors, the gravitational hearts that reside in the center of almost every large galaxy, including our own Milky Way. We can imagine the stellar mass black holes as individual trees, born from a single life cycle, while the supermassive ones are the vast, ancient forests that define the landscape, their origins dating back to the dawn of the universe itself, their growth shrouded in the mists of cosmic time. At the very center of our own swirling, spiral home, the Milky Way galaxy, about 26,000 light-years from Earth, in the direction of the constellation Sagittarius, lies our very own supermassive black hole. It is named Sagittarius A star, and while it is modest compared to the behemoth in M87, it is still a titan, containing the mass of approximately 4 million suns, compressed into a region smaller than the orbit of Mercury. This is the calm, silent heart of our galaxy, the central point of stability, around which all 100 billion stars, including our own Sun, are gracefully and patiently orbiting. It is not a menacing presence, not a cosmic monster waiting to devour us, but a fundamental component of our galactic home, a quiet and steady heartbeat that has likely been there since the galaxy's earliest days. Its immense gravity orchestrates the dance of the innermost stars and helps to anchor the grand, spiral structure of our galaxy. Thinking of this immense, silent presence at the center of our home can foster a sense of belonging and stability, a feeling of being part of a vast, orderly, and ancient cosmic city. The origins of these galactic hearts are one of the great unsolved puzzles in modern astrophysics, a story whose beginning we are still trying to piece together. How did they grow so massive, so quickly, in the early universe? One idea suggests they started as regular stellar mass black holes that, over billions of years, slowly grew by consuming gas, dust, and any stars that wandered too close, gradually merging with other black holes to become larger and larger. Another, more dramatic theory proposes that they were born from the direct collapse of unimaginably vast clouds of gas and dust in the primordial universe, forming directly as massive seeds of tens of thousands of solar masses, which then continued to grow. This profound uncertainty about their birth is not a failure of our science, but a source of deep wonder. It reminds us that we are looking back into the deepest reaches of time, trying to understand the childhood of our universe, and that some of its grandest secrets are still waiting patiently to be told. The mystery of their formation only adds to the silent, ancient majesty of these galactic anchors. Although Sagittarius A star itself is invisible, its presence is as certain as the sun in our sky, and we know this because we have witnessed its gravitational ballet. For over 2 decades, astronomers have used powerful telescopes to patiently track the movements of a small cluster of stars that orbit the galactic center at incredible speeds. One star in particular, named Stu, follows a long, elliptical path that brings it breathtakingly close to the central black hole. It completes one full orbit every 16 years, and at its closest approach, it travels at over 5,000 kilometers per second, nearly 2% of the speed of light. These impossibly fast and tight orbits, this celestial dance around an apparently empty point in space, can only be explained by the presence of an unseen object of immense mass and density. We cannot see the dance partner, but we can see the star's elegant and rapid waltz, and from its motion, we can precisely calculate the mass and location of the silent giant it orbits. It is a beautiful, indirect observation, a way of seeing the unseeable, not through its effect on light, but through its unwavering gravitational guidance of the stars, a silent cosmic conductor leading a celestial orchestra in the very heart of our home. As we watch these stars perform their rapid, silent waltz around the galactic heart, we are witnessing the profound curvature of space, but this immense gravity also warps a far more intimate and mysterious dimension, the gentle, flowing river of time itself. To understand this, we can begin with one of Einstein's most beautiful and intuitive insights, the principle of equivalence. He asked us to imagine being inside a small, sealed room with no windows. If you feel your feet pressed firmly to the floor, you cannot know for certain whether your room is resting on the surface of the Earth, held there by gravity, or if it is a rocket ship in deep space, accelerating upwards at a constant rate. The two sensations would be utterly indistinguishable. This simple thought experiment forges a deep and unbreakable link between gravity and acceleration, suggesting they are two different ways of describing the same fundamental phenomenon. It is a bridge of pure thought that connects the familiar feeling of being pushed back into your seat, as a car speeds up with the cosmic embrace that holds the moon in orbit around the Earth. This profound equivalence between gravity and acceleration leads to a startling and beautiful conclusion about the nature of time. We know from Einstein's earlier work on special relativity that time is not absolute, it is relative to the observer, and it can be stretched. For an object moving at very high speeds, time itself slows down. A clock on a speeding rocket will tick more slowly than a stationary clock. Now, if gravity and acceleration are truly equivalent, then what is true for acceleration must also be true for gravity. It must be that, in a strong gravitational field, where the acceleration of spacetime is immense, time itself must also slow down. This effect is known as gravitational time dilation. It is not a mechanical error in our clocks, but a fundamental property of the universe. Time is not a rigid universal metronome, ticking at the same rate for everyone, everywhere. Instead, It is a fluid, flexible medium, a great cosmic river that flows at different speeds in different places, its current dictated by the distribution of mass and energy. We can visualize this river of time flowing throughout the cosmos. Far away from any stars or galaxies, in the vast, empty interstellar spaces, the river flows broadly and swiftly, its current steady and unimpeded. But as it approaches a massive object like our Sun, the riverbed of spacetime deepens, and the current begins to slow. And as it flows nearer still to the edge of a black hole, the gravitational well becomes almost infinitely deep, and the river of time slows to a near-perfect standstill. To an observer, floating safely far away, anything falling towards the black hole would appear to be moving in slow motion, its journey taking longer and longer as it nears the edge. A thought experiment illustrates this most clearly. Imagine a pair of twins, where one journeys in a spaceship to orbit near the event horizon for what feels like a few hours to them, while the other twin waits on a space station far away. Upon returning, the traveling twin would find that decades, or even centuries, had passed for their sibling. Their few hours spent in the slow-moving currents of time near the black hole would be equivalent to a lifetime in the faster currents of the wider universe. This strange stretching of time is not just a theoretical curiosity. It is a measurable reality. We see its evidence in the light that travels to us from massive objects. Light, like any wave, has a frequency, a certain number of oscillations per second, which we can think of as the universe's most fundamental clock. As a photon of light climbs out of a deep gravitational well, it must expend energy, and in doing so, its frequency decreases, and its wavelength becomes longer, shifting it toward the red end of the electromagnetic spectrum. This effect, called gravitational redshift, is the light's own story of its struggle against gravity, a story told in the stretching of its very being. If we could watch a glowing clock fall into a black hole, we would see its light become progressively redder, and its ticks become progressively slower, stretching out over longer and longer intervals. The final tick, the final photon emitted just as it crosses the event horizon, would be stretched into an infinitely long wavelength, taking an infinite amount of time to reach us. It would simply fade, red-shifting into oblivion, its final moment suspended for all eternity from our perspective. A silent testament to the place where time itself comes to a gentle, endless halt. As this river of time slows to a near-perfect stillness at the silent shore of the event horizon, any object that dares to drift across this threshold begins a final transformation, a quiet and orderly deconstruction of its physical form. This process is driven by the very same force that governs the gentle, rhythmic rising and falling of our oceans here on Earth. The moon's gravity pulls on our planet, and its pull is slightly stronger on the side of the Earth facing it than on the far side. This difference in gravitational pull across the Earth's diameter causes the water to bulge on both the near and far sides, creating the predictable cycle of high and low tides. This stretching effect, born from a gradient in the gravitational field, is known as a tidal force. It is a gentle, constant presence in our world, a reminder that gravity is not a uniform force, but one that changes subtly with distance, a rhythmic breath that our planet takes twice each day in response to its lunar companion. Near a small, stellar mass black hole, these gentle tidal forces are magnified to an unimaginable degree. The gradient of the gravitational field near a small, dense object is incredibly steep. For any object falling towards such a black hole, the gravitational pull on the part of the object closer to the center is vastly stronger than the pull on the part that is farther away. This immense difference in force has a profound effect. It begins to pull the object apart, stretching it vertically, along the direction of the fall, while simultaneously squeezing it horizontally. This process, known by the somewhat playful name of spaghettification, is the ultimate act of gravitational deconstruction. But instead of imagining this as a violent and terrifying event, we can reframe it as a kind of graceful, cosmic unraveling. It is like watching a tightly woven piece of fabric being carefully unbraided, thread by thread, until only its constituent fibers remain. The object is not so much destroyed as it is simplified, its complex structure unwoven into a delicate, luminous stream of its fundamental atoms, a thin, flowing line returning to its most essential state as it merges with the singularity. Curiously, And perhaps counterintuitively, this fate is not immediate for all who approach a black hole. For the supermassive giants that sit at the centers of galaxies, the story is very different. Because their event horizons are so enormous, stretching for millions of kilometers, the gravitational gradient at this boundary is actually quite gentle. The difference in the pull of gravity between your head and your feet as you cross the event horizon of Sagittarius A star would be almost unnoticeable. An explorer could, in theory, drift across this point of no return peacefully and intact, feeling no immediate discomfort, completely unaware that they had just passed a cosmic threshold from which there is no escape. This transforms the gateway to the universe's largest abysses from a violent waterfall into a calm and deceptively gentle crossing. The true and final unraveling would still come, but it would happen much later, deep within the horizon, on the long, slow, and inevitable journey towards the central singularity. The crossing itself would be a moment of profound and eerie tranquility. While the interior of a black hole is a realm of silence and darkness, the region just outside the event horizon can be one of the most luminous and energetic places in the entire universe. As vast clouds of interstellar gas, dust, and the remnants of unfortunate stars are drawn in by the black hole's gravity, they do not fall straight in. Instead, because of the conservation of angular momentum, this material spirals inward, forming a vast, flat, rotating structure called an accretion disk. As the particles of gas and dust orbit at incredible speeds, they rub against each other, creating immense friction that heats the disk to millions of degrees, causing it to glow with a ferocious intensity across the entire electromagnetic spectrum, particularly in high-energy X-rays. So while the black hole itself is the epitome of darkness, its feeding process creates a spectacle of brilliant light. It is another of the universe's beautiful paradoxes. We find these points of absolute blackness by searching for these rings of unparalleled brightness, the final, luminous song of matter before it crosses the horizon and is forever silenced. This glowing, swirling disk is a final, energetic farewell, a last burst of heat and light before a final, cold plunge into the quiet unknown. For the longest time, our story of the black hole was a story of a final destination, a one-way journey into an eternal prison from which nothing could ever return. We pictured the event horizon as an ultimate seal, a permanent boundary between our universe and a realm of unknowable endings, where all the matter, light, and history that crossed it would be locked away forever. But the universe, especially when we listen to its faintest whispers at the smallest of scales, is a place of subtle and constant fluctuation, a reality far stranger and more fluid than it appears. And it is this quiet, quantum simmer, this gentle hum of potential in the heart of the void, that provides a way for even a black hole to breathe, to slowly and patiently whisper its existence back into the cosmos over unimaginable timescales. This discovery, a breathtaking marriage of gravity and quantum mechanics, transforms the black hole from a static endpoint into a dynamic, evolving entity with a life story all its own. To understand this gentle exhalation, we must first journey into the seemingly empty space of the vacuum. On a quantum level, this vacuum is not empty at all. It is a roiling, vibrant sea of potential, a quantum foam where energy is constantly fluctuating. These fluctuations allow for pairs of virtual particles and their corresponding antiparticles to spontaneously spring into existence from nothing, exist for an immeasurably brief moment, and then collide and annihilate one another, returning their borrowed energy to the vacuum. This is the hidden, subtle breath of the universe, a constant, gentle flicker of being and non-being that is happening everywhere, in every moment, throughout all of space. It is a fundamental process, the universe's background hum, a quiet but persistent reminder that even the most profound emptiness is filled with a restless creative energy, a promise of something from nothing, even if only for the briefest of instants. In the 1970s, the physicist Stephen Hawking wondered what would happen if one of these fleeting virtual particle pairs was born at the very edge of a black hole's event horizon. In this most precarious of locations, a strange and beautiful possibility emerges. It is possible for one particle of the pair, say the antiparticle, to fall across the horizon, while the other particle escapes into space. Once its partner is lost to the abyss, the escaping particle can no longer annihilate. It is orphaned, promoted from its fleeting virtual state into a real, tangible particle that travels away from the black hole. From the perspective of a distant observer, it would appear as though the black hole itself has just emitted a particle. This process, now known as Hawking radiation, is a beautiful and accidental act of creation at the edge of chaos. The black hole, in its silent and passive existence, inadvertently gives birth to a faint, steady stream of particles, a gentle glow of matter and light leaking from the very edge of its own darkness. This faint whisper of escaping particles has a profound consequence for the black hole itself. According to the fundamental laws of physics, energy must be conserved. Since the escaping particle carries positive energy away into the universe, the particle that fell into the black hole must be considered to have a kind of negative energy. This negative energy is subtracted from the black hole's total mass energy, meaning that with every single particle it emits, the black hole loses a tiny, almost infinitesimal amount of its mass. It is, in effect, slowly dissolving. This process of black hole evaporation is unbelievably slow for large black holes. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate, a timescale so vast that it makes the current age of the universe seem like the blink of an eye. This discovery completely changed our understanding of these objects. They are not eternal. They are finite, impermanent entities, destined to slowly fade away in a final, quiet whisper, returning all of their borrowed mass and energy back to the universe. They are like cosmic mountains, weathered away not by wind or rain, but by the gentlest possible breeze of quantum mechanics, over a timescale that redefines the very meaning of patience. This faint, almost imperceptible whisper of radiation, this slow evaporation that promises an eventual and final end for every black hole, opens a door to one of the deepest and most poetic puzzles in all of physics. It forces us to ask a profound question about the universe and its relationship with memory. Does the cosmos remember everything that happens within it? Or are some stories, once they fall into the abyss, truly and irretrievably lost forever? This is the heart of the black hole information paradox, a gentle but persistent contradiction that arises when our two great theories of reality, general relativity and quantum mechanics, try to tell the story of a black hole's life and death, and end up telling two very different tales. It is in this peaceful disagreement that we find a signpost, a quiet clue pointing toward an even deeper, more unified understanding of the universe that still lies beyond our horizon. At the core of quantum mechanics, there is a fundamental and reassuring principle. Information is never destroyed. In this context, information means all the intricate and specific details that define a physical object, the type of particles it is made of, their exact positions, their velocities, their quantum states. The principle of quantum determinism states that if we knew the precise state of every particle in a closed system, like the entire universe, we could in theory predict its exact state at any point in the future, and also reconstruct its exact state at any point in the past. Information is conserved. To make this feel more tangible, imagine writing a poem on a piece of paper and then burning it. It seems as though the information, the poem, has been destroyed. But according to physics, it hasn't. The information has simply been transformed and scrambled, encoded into the complex arrangement of the atoms in the smoke and ash, in the pattern of the heat radiated into the air. In principle, if one could gather every single particle and trace its path, the original poem could be reconstructed. The story is never truly lost, just very, very hard to read. Here, the paradox begins to take shape. According to general relativity and the no-hair theorem, when that piece of paper with the poem on it falls into a black hole, its information is lost to the outside universe, hidden forever behind the one-way door of the event horizon. The black hole itself, once it settles, remembers only the paper's mass, spin, and charge, while the poem itself is seemingly erased. Then, Stephen Hawking's theory tells us that the black hole eventually evaporates. The Hawking radiation it emits appears to be thermal and random, like the meaningless hiss of static. It contains information only about the black hole's mass, spin, and charge, not about the unique and specific things that fell inside to create it. So, when the black hole has completely vanished, taking its secrets with it, and the radiation it has left behind is random, what has happened to the poem? Where has its information gone? General relativity suggests it was lost inside, while quantum mechanics insists it cannot be lost at all. This is the paradox, a conflict between our best description of gravity and our best description of matter, a profound question about whether the universe ultimately keeps a perfect record of its own story. Physicists and philosophers have contemplated this gentle puzzle for decades, and while there is no final answer, some beautiful and mind-expanding ideas have emerged. One of the most prominent is the holographic principle. This idea suggests that the information about the poem on the paper is not lost within the singularity, nor is it immediately destroyed. Instead, as the paper falls in, all of its information is somehow imprinted or encoded onto the two-dimensional surface of the event horizon itself. The event horizon acts like a cosmic hologram, a lower dimensional surface that contains all the necessary data to describe the three-dimensional object that fell inside. Then, as the black hole slowly evaporates over trillions of years, this intricately stored information is subtly and carefully woven into the outgoing Hawking radiation. The radiation is not as random as it first appears. It is an incredibly complex and scrambled message, carrying the story of the poem back out into the universe. The universe, in this view, does not forget. It simply transforms its stories, re-encoding them in the faintest whispers of light and heat, ensuring that in the grand cosmic library, no book is ever truly, finally, burned. Beyond these profound questions of cosmic memory and the ultimate fate of matter, the supermassive black holes at the hearts of galaxies play a far more active and creative role in the present life of the cosmos, acting not as mere cosmic drains, but as powerful engines of regulation and change, much like a patient, cosmic gardener tending to a vast, celestial landscape. We have come to see them as the quiet, stable anchors of their galactic homes. But when a fresh supply of interstellar gas and dust is drawn into their vicinity, these sleeping giants can awaken into one of the most luminous and powerful phenomena in the universe. As this material spirals inward, the accretion disk can grow so vast and become so intensely hot that it shines with the light of 1 trillion suns, sometimes outshining all the stars in its host galaxy combined. These brilliantly illuminated galactic hearts are known as active galactic nuclei, or AGN, and the most powerful of them, seen from billions of light years away, are the quasars, the distant beacons of the young universe. This period of intense activity is not a sign of destruction, but of a vibrant and dynamic process, a demonstration that the black hole is not just a sink of matter, but a powerful engine capable of converting the energy of gravity into an astonishing torrent of light. From the heart of this swirling, luminous disk, another, even more dramatic structure often emerges. As the spinning black hole and its magnetic fields churn the superheated material of the inner accretion disk, they can act like a colossal cosmic accelerator, grabbing charged particles and launching them away from the black hole's poles in two narrow, focused, and opposing beams. These are relativistic jets, and they are among the largest and most energetic structures in the universe. They travel at speeds approaching that of light itself, blazing a straight path through their host galaxy and far out into the cold, empty space between the galaxies, sometimes stretching for hundreds of thousands of light years. They are like the focused beams of a cosmic lighthouse, a testament to the immense, ordered rotational energy of the central engine. These jets are the black hole's long-reaching arms, its way of interacting with its environment on a scale far beyond the immediate grasp of its gravity, a powerful and organized projection of its influence across a vast cosmic stage. This long-reaching influence creates a delicate and vital feedback loop between the central black hole and its host galaxy. The powerful winds of radiation from the hot accretion disk and the colossal jets pushing out into the galactic medium exert a tremendous pressure on the surrounding interstellar gas. This process, known as galactic feedback, is where we can truly begin to appreciate the black hole's role as a cosmic gardener. The jets act like a great celestial wind, blowing through the galaxy's spiral arms, and this wind can have a profound effect on the galaxy's ability to form new stars. In a galaxy rich with dense, cold clouds of gas, The rate of star formation might otherwise run rampant, quickly using up all the available material. But the energetic outflow from the central black hole can heat and disperse these clouds, effectively blowing away the raw material for new stars and preventing them from forming. The black hole is thinning the garden, preventing it from becoming overgrown and ensuring that its growth proceeds at a measured, sustainable pace. This gardening, however, is not a simple act of pruning. The relationship is far more complex and nuanced, as the jets can both suppress and trigger the birth of stars. While they may blow gas clear out of the smaller, central regions of a galaxy, quenching star formation there, the immense shockwaves they create as they plough through the interstellar medium can also compress other, more distant clouds of gas. This compression can be just the trigger needed to cause these clouds to collapse under their own gravity and ignite into fresh clusters of new stars. In this way, the black hole acts as a grand regulator of galactic life, a source of profound balance. It prunes in one area while seeding in another, helping to shape the structure, size, and star formation history of its galaxy over billions of years. This reveals a deep, symbiotic relationship, a coevolution where the growth of the central black hole and the growth of its host galaxy are intimately and inextricably linked. A quiet, cosmic dance of creation and regulation that unfolds over the grandest of scales. While we have come to see these stellar remnants and their supermassive cousins as fundamental architects of the cosmos, the universe may be populated with other, quieter classes of black holes, cosmic ghosts that drift through the great web of galaxies, their existence hinted at but not yet fully confirmed, representing the vast, unexplored territories in our understanding of these silent objects. Our journey can now take a turn into these more speculative realms, beginning with the very dawn of time itself. According to some theories, black holes did not need to wait for the first stars to be born and die. In the first few moments after the Big Bang, the universe was an unimaginably hot and dense place, a chaotic soup of energy and particles where the density was not perfectly uniform. In regions where the density was just slightly higher than average, the immense pressure of the primordial universe could have been enough to cause these regions to directly collapse under their own gravity, forming what are known as primordial black holes. These would be the true elders of the cosmos, not the children of stars, but the ancient relics of the universe's fiery birth, silent witnesses to nearly 13.8 billion years of cosmic history. These ancient, primordial black holes, if they exist, might offer a beautiful and simple solution to another of the universe's most profound mysteries, the puzzle of dark matter. For decades, we have observed that galaxies are spinning faster than they should, that clusters of galaxies are held together more tightly than we can account for. There seems to be a vast amount of invisible mass in the universe, a gravitational glue that we can feel but cannot see, which we have named dark matter. While many theories propose that dark matter is made of some new, exotic, undiscovered subatomic particle, another elegant possibility is that it is composed, at least in part, of these primordial black holes. If a vast number of these objects were formed in the early universe, with masses perhaps similar to that of a small asteroid or a large mountain, they would now be drifting silently through the cosmos, completely invisible to our telescopes, yet collectively exerting the immense gravitational pull needed to explain our observations. It is a wonderfully poetic idea, that the universe's greatest missing mass is not something new and strange, but simply the oldest, darkest, and most compact of objects, hiding from us in plain sight. Between the well-established domains of the stellar mass and the supermassive, there lies a mysterious gap, a missing link in the black hole family, the intermediate mass black holes. These are theoretical objects with masses ranging from 100 to a few 100,000 times that of our Sun, and they have proven to be exceptionally elusive. They are too massive to have formed from the collapse of a single, ordinary star, yet they are not nearly massive enough to be the gravitational anchors of large galaxies like our own. They are the cosmic nomads, the shy hermits of the black hole world. The search for them has focused on the dense, ancient hearts of globular clusters, which are tightly packed, spherical collections of hundreds of thousands of old stars orbiting a galaxy. It is thought that within these dense stellar cities, repeated collisions and mergers between stars and smaller black holes could have built up an intermediate mass black hole over time. Finding them would fill a critical gap in our theories of black hole evolution, showing us how the stellar seeds might eventually grow into the supermassive giants. Our speculative journey can even take us to the smallest conceivable scales, to the realm of micro black holes. Some theories that go beyond our current understanding of physics, such as those involving extra dimensions of space, suggest that it might be possible to create microscopic black holes in high-energy particle collisions, for example, in particle accelerators here on Earth. However, these theories also predict that such tiny black holes would be incredibly unstable. According to Hawking's theory of evaporation, the smaller a black hole is, the hotter it is, and the faster it radiates its mass away. A microscopic black hole would be so astonishingly hot that it would evaporate in a tiny fraction of a second, disappearing in a harmless puff of particles. While they remain purely theoretical, they represent the outer limits of our imagination, stretching our understanding of gravity into new and uncharted territory. And as we contemplate this full cosmic zoo of silent objects, from the smallest theoretical sparks to the largest galactic hearts, we can appreciate that our knowledge has been built on seeing their effects on matter and light. But the universe has recently gifted us with an entirely new sense, a new way to listen to their most silent and most dramatic cosmic songs. This new sense, this new way of listening to the cosmos, does not rely on light or matter, but on the very fabric of space-time itself, for it was a century ago that Einstein first realized that this fabric could not only bend, but that it could also ripple, that it could carry waves much like the surface of a still pond disturbed by a falling stone. He predicted that any massive object accelerating through space-time would create these disturbances, these gentle shivers in the geometry of the universe, which we now call gravitational waves. For most of a century, this idea remained a beautiful but unproven piece of his theory, as the waves produced by anything in our solar system would be far too faint for us to ever detect. But the universe holds events of unimaginable scale and power, events so cataclysmic that their silent reverberations can travel across the cosmos for 1 billion years to finally wash over us, and it is in these events that we have finally learned to hear the silent ringing of space-time. These gravitational waves are not like sound waves, which are vibrations of air that travel through space. They are vibrations of space itself. As a wave passes by, it gently and rhythmically stretches and squeezes the space it moves through, and everything contained within that space. The effect is impossibly subtle. A gravitational wave passing through your body right now would stretch you in one direction while squeezing you in another by an amount 1,000 times smaller than the nucleus of a single atom. We feel nothing. We see nothing. It is the universe's most profound and understated form of communication, a message carried not by light, but by the very medium of reality. And the most powerful sources of these waves are the most dramatic and silent events the universe has to offer. The final, intimate dance and merger of two black holes. Imagine two of these silent, dark objects, born from long-dead stars, caught in each other's gravitational embrace. Over millions of years, they orbit one another, their dance slowly tightening, their speed ever increasing as they radiate away their orbital energy in the form of these gentle gravitational waves. In the final moments of their lives, these two black holes are whipping around each other hundreds of times per second, stirring the fabric of space-time into a violent, churning storm. The waves they emit become stronger and higher in frequency, a rising crescendo that carries away an amount of energy so vast it briefly outshines all the light from all the stars in the observable universe combined. And yet, this event of almost unimaginable power occurs in perfect and complete silence. Its only evidence a final, powerful burst of gravitational waves that propagates outward in all directions at the speed of light. Then, in an instant, the two event horizons touch and merge, becoming a single, larger, more massive black hole. The wild churning of space-time ceases, and the new, unified black hole quickly settles down, its quivering surface emitting a final few calming waves, a ring down like the fading chime of a gently struck bell. This whole spectacular event, from the final in-spiral to the quiet ring down, is a cosmic story told only in the language of pure gravity. To hear this silent story, humanity built some of the most sensitive instruments ever conceived. Observatories like LIGO and Virgo are not telescopes that look at the sky, but vast, L-shaped detectors that listen to the vibrations of space. They work by splitting a single laser beam and sending it down two long, perpendicular tunnels, each several kilometers in length, to be reflected by mirrors at the ends. When the two beams are recombined, they are perfectly aligned. But if a gravitational wave passes through the detector, it will stretch one arm while squeezing the other, knocking the laser beams ever so slightly out of alignment and creating a telltale signal. And on September 14th, 2015, it happened. A clear, beautiful signal washed over the detectors, a perfect chirp that rose in frequency and amplitude, the unmistakable sound of two black holes, 36 and 29 times the mass of the Sun, merging in a distant galaxy 1.3 billion years ago. For the first time, we did not see the universe. We heard it. We heard its silent drumming, and in that moment, a new era of astronomy was born. An era where we can finally perceive the cosmos in its darkest and most silent moments of transformation. When these two silent dancers finally merge into one, the newly formed, larger black hole is left in a state of immense and rapid rotation, a spinning giant that now imposes a new and even stranger structure on the spacetime around it, a cosmic whirlpool of pure geometry. For most of our journey so far, we have pictured a black hole in its simplest form, a non-rotating, perfectly spherical object, described by the solutions of Carl Schwarzschild. This is a beautiful and useful idealization, but in the real universe, it is almost certain that nearly all black holes spin. They inherit the angular momentum of the massive star that collapsed to form them, or they gain it from the orbital energy of the very mergers that we can now hear with gravitational waves. This spin adds a wonderful new layer of complexity and dynamism to the black hole. It is no longer just a static, passive well in the fabric of spacetime, but an active, twisting vortex. The spacetime around it is not just curved, it is being actively dragged along, a silent cosmic storm in which the familiar rules of space and motion are beautifully and profoundly warped. This effect, known as frame dragging, is one of the most fascinating predictions of Einstein's theory. Imagine a heavy ball spinning rapidly in a vat of thick, clear honey. As the ball spins, its motion drags the honey closest to it along for the ride, creating a swirling vortex that becomes less pronounced farther away from the ball. A rotating black hole does the exact same thing to the very fabric of space-time. It twists the space around it into a great, silent whirlpool. Anything that falls toward a spinning black hole does not just fall straight in. It is caught in this current and forced to spiral around it. This is not a suggestion. It is a fundamental property of the space in this region. The universe itself is in motion here, an elegant, ordered flow that every particle of matter and every ray of light is compelled to join. It is a cosmic waltz where space-time itself is the dance floor, and the spinning black hole is the silent, tireless conductor. This dragging of space-time creates a strange and wondrous region outside the event horizon known as the ergosphere. It is a flattened, pumpkin-shaped area that touches the event horizon at the poles and extends farther out at the equator. Within this region, the dragging of space-time is so extreme that it is moving at the local speed of light. The consequence of this is extraordinary. Inside the ergosphere, it is physically impossible to stand still. To remain in one place relative to the distant stars, an object would have to travel faster than the speed of light against the current of space-time, which is impossible. And so, everything within the ergosphere is forced to rotate in the same direction as the black hole. It is a place of compelled, perpetual motion, a gentle but irresistible cosmic current from which there is no stillness. But unlike the event horizon, the ergosphere is not a point of no return. It is possible to enter this region and then leave again, as long as one does not cross the event horizon that lies within it. This accessibility makes the ergosphere a region of immense theoretical interest, a place of almost unimaginable, ordered energy. It is like a colossal cosmic flywheel, storing a vast amount of energy in the pure rotation of the black hole. The physicist Roger Penrose conceived of a famous thought experiment, now called the Penrose process, for how one might theoretically tap into this energy. He imagined a probe entering the ergosphere and then splitting into two pieces. If one piece is directed to fall into the event horizon, the other piece can be ejected from the ergosphere with even more energy than the original probe had when it first entered. This extra energy is, in effect, stolen directly from the black hole's rotational energy, causing it to spin down by an infinitesimal amount. While this remains a purely theoretical concept, it is a beautiful one. It reframes the black hole not just as a consumer of matter and energy, but as a potential source of it, a vast, silent battery whose power is stored in the simple, elegant perfection of its spin. And as we contemplate these strange mathematical boundaries, from the still shore of the event horizon to the swirling currents of the ergosphere, our minds are naturally drawn to wonder if these gateways could lead to even stranger places and possibilities. As our journey of the mind takes us to these strange and swirling boundaries of space-time, we are naturally invited to step beyond the edge of observation and into the beautiful, dreamlike realms of pure mathematics, asking not just what a black hole is, but what it could be, what it could connect to. When physicists first began to explore the elegant equations of general relativity, they discovered that the mathematical description of a black hole contained a hint of something strange and wonderful. The simplest solution for a non-rotating black hole, when followed to its most logical and complete conclusion, did not just describe a gateway to a singularity, it also described a theoretical gateway out again, a corresponding entity known as a white hole, with the two ends connected by a narrow channel through space-time. This theoretical connection, known as an Einstein-Rosen bridge, is the original and most famous concept of a wormhole. We can think of this not as a physical reality, but as a beautiful and hidden poem found within the language of the universe, a whisper of cosmic connection written into the very mathematics that describe gravity. A white hole, in this mathematical dream, is the perfect, time-reversed mirror of a black hole. It is a hypothetical region of space-time which nothing can enter from the outside, but from which matter, energy, and light are able to escape. Where a black hole is a cosmic drain, a white hole would be a cosmic fountain, a place from which things can only ever flow outwards. It is a profoundly symmetrical and aesthetically pleasing idea, the universe providing a perfect counterbalance to its darkest creations. If a black hole is the ultimate inhale, a gathering of all things into a single point, then a white hole would be the ultimate exhale, a spring of matter and energy flowing out into the cosmos. While we have no observational evidence that white holes exist, and good theoretical reasons to doubt that they can form in our universe, they remain a beautiful piece of the theoretical puzzle, a reminder that the laws of physics often possess a deep and satisfying symmetry, a perfect balance of opposites. However, this beautiful vision of a cosmic shortcut, a bridge from a black hole in one part of the universe to a white hole in another, comes with a profound and gentle caveat. According to the same mathematics that describes its existence, this simple type of wormhole would be incredibly unstable. The throat of the bridge would be so fragile that it would pinch off and collapse into a singularity the very instant it formed, or the moment even a single photon of light attempted to travel through it. It is a connection that is predicted to last for no time at all. This fragility does not necessarily make the idea less compelling, it transforms it into something more poetic and fleeting. The Einstein-Rosen bridge is a perfect, theoretical connection that can only exist in an equally perfect and undisturbed mathematical state. It is like a path made of morning mist, or a bridge spun from a delicate soap bubble, a thing of immense beauty in its potential, but far too ephemeral and fragile to ever bear the weight of a single traveller. It is a connection that can be contemplated, but perhaps never made. To overcome this inherent instability, to hold the throat of the wormhole open long enough for something to pass through, our theories suggest that we would need something truly extraordinary. We would need a form of matter with properties unlike anything we have ever discovered, a substance often called exotic matter. This hypothetical material would need to have a negative energy density, which means it would have to possess a kind of anti-gravity, pushing space-time apart rather than pulling it together. Such a substance would be needed to line the walls of the wormhole, to prop it open against its own catastrophic tendency to collapse. This places the idea of a traversable wormhole firmly into the realm of deep and peaceful speculation, a gentle what-if scenario that allows our minds to drift and wander on the edge of sleep. It is an invitation to imagine a universe with different rules, where matter itself might have a gentle, opposite nature, a push instead of a pull. And as our journey through the physics of the black hole comes to a close, from the familiar lives of stars to these distant, speculative shores of the imagination, we can now allow our minds to turn inward, to contemplate not the mechanics of this profound darkness, but its deep and calming meaning. Having journeyed through the physics and the mathematics, through the known and the imagined, we can now let these ideas settle and allow our focus to drift away from the science of the black hole and towards its silent, aesthetic poetry, towards the deep, calming meaning of the void itself. Our contemplation can begin with a simple, sensory fact. A black hole is the most perfect black object in the entire universe. It is a perfect absorber, a true black body that takes in every single photon of light, every wavelength of radiation that happens to strike its event horizon, reflecting absolutely nothing. The color of a black hole is not just a dark shade of grey, it is a fundamental and absolute absence of light. In this perfect blackness, we can find an echo of the profound peace that comes from sensory stillness. Think of the deep comfort of a perfectly dark and quiet room at the end of a long day, a space where your senses are finally allowed to rest, where there is nothing to see, nothing to process. The black hole's color is the color of deep rest, of a quiet and receptive state. It is the ultimate blank canvas, a patch of perfect calm that, by its very contrast, allows the luminous beauty of the surrounding stars and galaxies to shine all the brighter. This idea of a deep, receptive darkness can be extended from a sensory experience to a psychological one. The black hole can serve as a powerful and gentle metaphor for the deep, unknown, and often unexamined parts of our own minds, the vast and mysterious realm of the subconscious. In many psychological traditions, this inner darkness is not something to be feared or avoided, but is seen as a source of immense power, intuition, creativity, and wisdom. Like the unseen gravity of a black hole that shapes the orbits of the stars, our subconscious has a quiet but powerful influence on our conscious thoughts, feelings, and actions. The invitation, then, is not to try and shine a harsh light into every corner of this inner space, but to learn to sit peacefully with its mystery, to trust the quiet wisdom that can emerge from our own inner silence. Embracing this personal void can be a path to profound self-acceptance and a deeper understanding that our wholeness includes not just the light of our awareness, but the deep, quiet darkness from which it arises. This beautiful relationship between form and emptiness is a cornerstone of great art. In painting, sculpture, and design, the concept of negative space is a vital tool. The empty space around and between the subjects of an artwork is never truly empty. It is an active and essential component of the composition. It is the negative space that gives definition, balance, and meaning to the positive space. The Japanese aesthetic concept of ma speaks to this beautifully, referring to the artistic interpretation of this empty space, the pause in a piece of music, the blank interval in time and space. The black hole is the universe's grandest expression of ma. It is the ultimate pocket of cosmic negative space, and its dark, silent silhouette gives shape and context to the luminous swirl of a galaxy. Its profound silence makes the gentle light of the stars seem all the more precious. It is a cosmic meditation on the importance of emptiness, of the quiet pauses in our own lives, the moments of rest, of reflection, of simply being that give shape, meaning, and beauty to the busier, more active parts of our days. This brings us to a final, philosophical contemplation of the void. In many Eastern and mystical traditions, the concept of nothingness, or sunyata in Buddhism, is not a terrifying abyss of non-existence. Instead, it is seen as the ultimate reality, a state of pure, boundless potential from which all forms and phenomena arise, and to which they all eventually return. From this perspective, the black hole is not a destroyer of things, but a transformer, a gateway back to this state of pure potentiality. The matter that falls across the event horizon is stripped of all its complex form, its intricate history dissolved, as it returns to a simple, unified state at the singularity. We can see this not as an end, but as a deeply calming and natural process of letting go. It is a cosmic release of complexity, a return to a fundamental and peaceful unity. The void, then, is not empty. It is a fullness, a quiet and generative womb of all possibility, a silence that is not empty, but is instead full of stars. This philosophical idea of a natural, peaceful return to a state of profound simplicity finds its perfect scientific counterpart in one of the most fundamental and often misunderstood laws of the physical universe, a law that governs the inexorable flow of time and the inevitable journey of all things towards a state of quiet and perfect equilibrium. This is the second law of thermodynamics, and its central concept is entropy. The word is often simply defined as disorder, but a more gentle and intuitive way to understand it is as the universe's natural tendency for energy to spread out, for things to move from concentrated, unlikely arrangements to more diffuse, more probable ones. It is not a prescription for chaos, but a description of a natural, calming process of settling. We witness this law in action in the simplest and most peaceful of moments. The slow and irreversible way a drop of dark ink spreads throughout a still glass of water, transforming from a single, ordered point into a uniform, pale cloud. We feel it as a cup of hot tea on a quiet evening naturally and gently cools, sharing its concentrated heat with the surrounding air until it reaches a perfect balance, a shared temperature with its environment. Entropy is the universe's deep and calming sigh of release. For a long time, black holes seem to present a profound challenge to this fundamental law. If entropy always increases, what happens when you throw something with high entropy, like a cup of hot tea, into a black hole? The tea vanishes, and its entropy seems to vanish with it, seemingly violating the second law. The solution to this puzzle, discovered through the work of physicists Jacob Bekenstein and Stephen Hawking, is one of the most beautiful and profound syntheses in all of science. They discovered that black holes themselves possess entropy, and in fact, they are the most entropic objects in the entire universe for their size. They found that a black hole's entropy is not proportional to its volume, but is instead directly proportional to the two-dimensional surface area of its event horizon. This is a staggering and beautiful result. It suggests that all the information about the immense, complex, three-dimensional interior of a black hole, all the stories of the stars and planets that fell inside, is somehow encoded on its silent, two-dimensional boundary, just as we explored in the holographic principle. The black hole is the ultimate state of thermodynamic equilibrium, a place where all the concentrated energy and ordered matter that has fallen in has been perfectly and completely thermalized, reaching a state of maximum, peaceful simplicity. This deep connection between black holes and entropy also illuminates the nature of time itself. The second law is what provides the universe with its arrow of time, the reason why we experience time as flowing in one direction, from the past, through the present, and into the future. We can remember the past, but not the future, precisely because the universe as a whole began in a very special, highly ordered, low-entropy state at the Big Bang, and it has been moving towards states of higher entropy ever since. The ink spreads out in the water, but we never see it spontaneously gather itself back into a single drop. The cup of tea cools, but it does not spontaneously draw heat from the room to become hot again. This constant, one-way journey towards equilibrium is woven into the very fabric of our experience of reality, and it is this journey that we call the passage of time. In this grand cosmic story, black holes play a crucial role as the guarantors of time's arrow. By taking in ordered matter and energy and converting it into a state of maximum entropy, they are powerful engines driving this universal process forward. They are the ultimate endpoints of the thermodynamic journey for any matter that they capture, ensuring that the universe's overall trend towards equilibrium is upheld. In a deep and fundamental way, the existence of these silent, simple objects is linked to the familiar, forward flow of our own lives. They are not just strange, distant objects, but are woven into the very causal fabric of the cosmos, their immense entropy helping to underwrite the gentle, one-way river of time that carries us all. And as we contemplate this image of the black hole as a perfect state of final rest, a quiet embodiment of this universal law, we can begin to see that this endpoint is not truly an end, but merely one phase in an even grander, slower, and more magnificent cosmic story. And so, as we hold in our minds this image of the black hole as a place of ultimate rest, a perfect state of entropic calm, we can now weave it together with the faint, patient whisper of Hawking radiation to see not an end, but a grand and magnificent cosmic cycle, a story of dissolution and rebirth on a timescale that transcends all human comprehension. This cycle has two great, opposing movements, like a slow, cosmic breath that takes an eternity to complete. The first movement is the inhale, the process of accretion, the gathering of matter and energy. Over millions and billions of years, the black hole acts as a patient and silent steward, a cosmic custodian, carefully drawing in the dust, gas, and stars from its surroundings. It gathers this complexity, this order, this light, and holds it in a state of deep, quiet suspension behind the veil of its event horizon, transforming it all into the simple, perfect entropy of its own being. This is the gathering phase, the period of growth, the slow and steady accumulation that builds these silent giants into the anchors of their galaxies. The second movement of this cosmic breath is the long, slow, and gentle exhale, the process of Hawking radiation. This is the returning phase, the quiet and generous act of giving back. Over timescales that dwarf the current age of the universe, the black hole patiently and steadily breathes its stored essence back out into the void. It is a process of almost unimaginable slowness, a whisper of low-energy photons and other particles that are the faint echo of all that the black hole has consumed. This gentle radiation ensures that nothing is held captive forever, that the universal laws of conservation and transformation are ultimately honored. The black hole is not a permanent prison, but a temporary vessel, a profound and patient transformer that holds onto its contents for an age, only to release them back into the cosmos in a new, simpler, and more diffuse form. The inhale is the journey into unity and simplicity. The exhale is the return journey back into the vast, open potential of the universe. To speak of the timescales of this cycle is to touch the face of infinity. For a black hole with the mass of our Sun, the time it would take to completely evaporate through Hawking radiation is around 10 to the power of 67 years, a 1 followed by 67 zeros. For the supermassive black holes at the hearts of galaxies, the timescales are even more staggering, stretching to a Google years and beyond. These numbers are so colossally large that they render all of human history, all of life on Earth, the entire age of the universe itself, into an insignificant, fleeting instant. There is a deep and profound calm to be found in contemplating such vastness. It places all of our earthly worries and hurried schedules into a grand and peaceful perspective. It speaks to a universe of almost infinite patience, where the most fundamental cycles of creation and dissolution unfold with an unhurried, silent grace that is far beyond our immediate experience, but not beyond our quiet contemplation. And what of the very end of this cycle? As a black hole radiates away its mass, it shrinks, and as it shrinks, its temperature rises and its rate of evaporation accelerates. In its final moments, having dwindled to the mass of a mountain and then to less than a gram, this process runs away catastrophically. The last of its mass is converted into energy in a final, quiet, but intense flash of high-energy gamma rays. This will be the last glimmer of light in the distant, far future of our universe. In the era known as the heat death, when all the stars have long since burned out and all matter has decayed, the universe will be a cold, dark, and vastly expanded place. The only interesting events left will be the final, gentle goodbyes of the last remaining black holes, their slow evaporation, and final, soft flashes of light being the last meaningful sighs of a cosmos that is finally settling into a state of perfect, eternal, and peaceful equilibrium. And yet, this vision of an end is also a vision of continuity. It is a universe where nothing is ever truly destroyed, only endlessly and patiently transformed. A final, comforting thought as we prepare to turn this cosmic journey inward to the universe that lies within each of us. This grand cosmic cycle of gathering and returning, of complexity, dissolving into a peaceful unity, provides us with our final and perhaps most profound metaphor, for our journey through the stars has ultimately been a mirror, and now we can turn that mirror inward to contemplate the silent, mysterious, and powerful universe that resides within the quiet depths of our own minds. Just as the vast majority of the cosmos is made of dark matter and dark energy that we cannot see but can feel the effects of, the vast majority of our own mind is the subconscious, a deep and powerful realm that quietly shapes our conscious experience. The event horizon of a black hole, that silent, one-way shore, can be seen as the gentle boundary between our waking, conscious awareness and this deeper, subconscious self. Throughout our days, experiences, thoughts, and feelings fall across this horizon, sinking from our immediate attention into the quiet depths of our memory and being, where they are stored, integrated, and transformed in ways our conscious mind may never fully understand. This is not a process of loss, but of integration, and we can learn to trust this process, to feel a sense of peace in knowing that there is a deep and powerful part of us, like a silent gravitational center, that is constantly working, dreaming, and organizing our inner world, even and especially when our conscious mind is at rest. At the heart of this inner universe, we can imagine our own singularity. This is not a point of infinite density, but a point of infinite mystery. The core of our own being, the fundamental I that we can never fully grasp or define with language or rational thought. We spend so much of our lives trying to analyze and understand ourselves, to create a stable and coherent story of who we are. But perhaps the greatest peace comes from accepting that at our very center there is a beautiful and necessary mystery. The core of our consciousness is not a problem to be solved, but a presence to be experienced. Like the singularity of a black hole, it is a place where our words and concepts fall silent. Accepting this allows us to let go of the need to have everything figured out, to find a deep and abiding comfort in the simple, quiet fact of our own mysterious existence. A mystery that we are here not to solve, but simply to inhabit. With this gentle acceptance, we can find a new way to relate to the swirling contents of our own minds. We can learn to orbit them peacefully, like a planet in a stable, distant orbit around a great, central star. Imagine, as you lie here, that your thoughts, your worries, the memories of your day are like the dust and gas in a luminous accretion disk. They swirl, they glow, they can be intense and bright. The practice of mindfulness, of quiet meditation, is the practice of finding a safe and stable orbit around this activity. It is the art of observing the swirl without being pulled into it, of acknowledging the presence of a thought or a feeling without becoming that thought or feeling. You can watch them from a place of quiet, detached stillness, noticing their colors, their textures, their energy as they drift by. You do not have to fall into the disk. You can simply be the quiet, witnessing presence that is aware of the swirl, and in that awareness, you can find a vast and liberating space of inner peace. Finally, we can fully embrace our own inner void, not as an emptiness to be feared and filled, but as a vital and necessary sanctuary for rest and renewal. In our modern world, we are so often encouraged to be constantly active, constantly processing, constantly taking in information. We can come to fear, silence, and stillness. But the black hole teaches us the power and beauty of a receptive and quiet state. To consciously create moments of inner quiet, to unplug from the noise and allow ourselves to drift into our own inner darkness, is a profound act of self-care. It is in this inner void that our minds and bodies truly heal and recharge. It is the space where our subconscious can do its deepest work of integration and problem-solving. And often, it is from this place of deep, quiet rest that our most creative insights, our most gentle intuitions, and our deepest sense of well-being can emerge, like a faint and beautiful whisper of Hawking radiation, a gift from the quiet, generative darkness within. This silent, inner universe is not a place to escape from, but a peaceful home to which we can always, and finally, return. And so, our long, quiet drift through the cosmic dark comes to a gentle close, having found in the heart of the universe's greatest mystery not a void of terror, but a profound and comforting silence a silence that echoes in the quietest corners of our own being. We began our journey in the luminous, vibrant chaos of a stellar nursery, a cosmic cloud of pure potential. We watched a great star awaken, live its brilliant life, and die in a magnificent, final, silent firework, a supernova that seeded the cosmos with the very elements of life. From its serene and quiet ashes, a new presence was born, a point of pure gravity, a black hole. We learned to see this invisible object, not with our eyes, but with our understanding, witnessing how it bent the fabric of space-time, creating a gentle landscape for planets to follow, and a powerful lens to warp the light of distant galaxies. We drew near its silent shore, the event horizon, and contemplated the strange, beautiful slowing of the river of time, a place where a moment could stretch into an eternity. We saw that this place of ultimate consumption was not eternal, that it had a life of its own, whispering its essence back into the universe over a timescale of almost infinite patience. Throughout our journey, the black hole has transformed in our minds. It ceased to be a simple, static object of destruction, a cosmic vacuum cleaner in the dark. Instead, it became a dynamic and vital architect of the cosmos. We saw it as a cosmic gardener, its powerful jets and winds regulating the birth of stars and shaping the destiny of its entire host galaxy in a delicate, symbiotic dance. We saw it as a cosmic library, its surface potentially holding a holographic record of all the stories that have fallen into its embrace, a testament to a universe that may never truly forget. And finally, we saw it as a cosmic steward, a patient custodian of matter and energy, holding them in a state of perfect, entropic peace, before slowly, gently, returning them to the universe in a grand cycle of dissolution and renewal that ensures nothing is ever truly lost, only transformed. Our journey has not been about finding answers to every mystery, but about learning to rest peacefully within the questions themselves, to find a deep comfort in the vast and beautiful quiet of the unknown. In this way, our exploration of the cosmos becomes more than just an accumulation of facts. It becomes a source of deep and personal meaning. The pursuit of scientific knowledge, at its heart, is a deeply human and poetic quest. It is a way of looking out into the vast, silent darkness of the night and seeing not an empty and indifferent void, but a place of profound order, intricate connection, and breathtaking beauty. It is a way of writing new and better stories about our place in the universe, stories that can inspire us, humble us, and ultimately bring our minds a sense of peace and perspective. In understanding the immense and patient life cycle of a black hole, we can find a new perspective on the hurried pace of our own lives. In contemplating the silent, gravitational heart of our galaxy, we can find a sense of belonging to something vast, ancient, and wonderfully stable. And so, as we prepare now for the final, gentle drift into sleep, we can hold on to this lasting and peaceful image. A universe underpinned not by chaos and noise, but by a deep, resonant, and meaningful silence. The darkness of the night sky is not an emptiness, but a fullness, a canvas filled with these watchful, silent presences that create and shape and guide the cosmic dance. It is a silence full of stars, a peace that passeth all understanding. May your own inner universe be just as peaceful tonight. Thank you for joining me on this journey into the quiet heart of the cosmos. I hope it has brought you some measure of calm and wonder. If you have enjoyed our time together, I would be so grateful if you would share a gentle thought in the comments below, or perhaps a suggestion for a future journey. Your support in the form of a like and a subscription helps these stories reach others who might be seeking a peaceful rest. Thank you so much. May your sleep be deep and your dreams be filled with the quiet light of a billion distant stars. Good night.